This meeting is being recorded.
So welcome to today's good seminar. Today's speaker is Kateřina Trlifajová, who will speak about sizes of countable sets.
Good afternoon. Thank you for your invitation. I am glad I have an opportunity to speak about my topic here in my faculty. And moreover, I have a tiny hope that somebody can use or will say me how to use my research. So we'll see. Sizes of countable sets. Maybe it's a nonsense because all countable sets have the same size, namely they have cardinality L0. However, the question of sizes of countable sets is connected with the question of infinity, of the existence of infinity, and of the question how to compare infinite collections. So there are two great questions concerning infinity. First, it is the existence of actual infinity. There were two great defenders of it. It was Bernard Bolzano, our Czech philosopher and mathematician, and Georg Cantor. The both of them agreed with the existence of actual infinity. The other question is how to measure infinities. What are their sizes? The problem of measuring infinities and comparing their sizes is maybe best illustrated by the famous Galileo's paradox. We compare the size of all natural numbers and of all of their squares, 1/4 of their second powers. On one side, there are less squares than natural numbers because only some numbers are squares. But on the other side, for every number, we can find its square, or 1, 1, 2, 4, etc. So from this point of view, there are as many squares as numbers. When we consider two well-known principles, one of them is already Euclid's principle. It is one of Euclid's axioms. It's called part-whole principle that says that the whole is greater than its part. So according to this principle, there are less squares. However, when we take Cantor's principle that says that from one-to-one correspondence follows equality of elements of two sets. So according to Cantor's principle, there are as many squares as numbers. And every scholar who wants to work with infinity must choose one of these principles. So while as it is well known, Cantor uses his Cantor's principle, of course. Bolzano, he preferred part-whole principles. He didn't. So, for instance, here is one of his quotation from Paradoxes of the Infinite from 1848, when he speaks about one-to-one correspondence as of a highly remarkable peculiarity. And then he describes one-to-one correspondence, but he says that merely from these circumstances, we can in no way conclude that these two multitudes are equal to one another. And he continues, an equality of these multiplicities may only be concluded if some other reason is added, such as that both sets have one and the same determining ground, or the same way of being formed. But he doesn't, already Bolzano doesn't define exactly what is the meaning of determining ground. Sometimes he says, he uses it in some examples, but he doesn't provide the exact mathematical definition. When we look from this point of view at Galileo's paradox, so in this paradox there is a hidden question, and it is, what is the determining ground of the squares? How do we get the squares? There are two possibilities. Either we select them from numbers, and then there are less squares than numbers, or we create them from numbers. In fact, in Zermelo-Fraenkel set theory, there are two axiom schema how to form a new set or how to form a set of squares. The first one is this axiom schema of specification that says that when we have a set, we can form a subset of elements with a special property. So by this axiom schema, we take the set of all natural numbers such that there exists a number m such that this number is a square of another of that number m. This is the schema of specification, and according to intuitively, it would be less squares than numbers. But another scheme of replacement, when we make, it says that we can make an image of a set. And because natural numbers is a set, its image is also a set. Of course, in Zermelo-Fraenkel set theory, A equals B. There is no difference. They are the same because it uses the Cantor's principle for comparison of sets. However, we would like to find a method how to describe sizes of countable sets such that the part-whole principle is valid. I would like to return to Bolzano's paradoxes of the infinite because Bolzano wanted to make a set theory with where the part-whole principle is valid. So in this book, Bolzano works with infinite series like this. For instance, series the sum of 1 plus 2 plus 3, etc., or not by chance the sum of squares, or he has a series of only units, or he has another series. It is similar as the previous one. However, the first m terms are omitted. And from his way of treating these infinite series, we can conclude several principles that Bolzano uses. First is that infinite series have one and the same multitude of terms. They finish by suffix in. And Bolzano says that all these series have one and the same multitude of terms. Second, unless explicitly stated otherwise, as in the case of these two series. And then he asserts that the difference between these two series is exactly m. Then it is possible to compare two series, for instance, S and P, when we can compare every corresponding term. And because every corresponding term of S is greater than that in P, so we can conclude that S is greater than P. And we can even say that S is infinitely greater than P, because he counts it really, that S is greater than every finite multiple of P. Yes. It is his definition that one quantity, he speaks about quantities, about these series as quantities, and he demonstrates how to work with these quantities. And the last one, if we change the order of finitely many terms of the series, then the quantity doesn't change. So it's possible to change. In fact, associative and commutative law is valid for finite number of terms. So the first question is it possible to make a meaningful interpretation, of course, in our usual set theory, because we don't want to create new set theory. So it is possible to interpret it as non-decreasing sequences of partial sums, usual way of working with infinite series. So we interpret it as non-decreasing sequences of partial sums So the first one corresponds as this sequence, etc. Here, this is n minus n. One, this is as the sequence 1, 2, 3, 4, and this is the same sequence but minus m. And if yes, of course, in this interpretation also we can use any finite number m as an infinite sequence that continues only by m. And when we define on these sequences sum and product component-wise, yes, we define it addition and multiplication component-wise, then we can define equality by this way: the two sequences are equal when they are equal from a sufficiently great index. If there is a, for instance, m, that for all n greater than m, the terms are equal. By the same way, we can define order, that one sequence is less than another sequence when their terms are less from sufficiently great index. And moreover, we can also define that one sequence is infinitely less than another one when it's for every natural numbers, yes, it is for every finite natural numbers, k times this sequence is less in this comparison than another sequence. In fact, I don't know how far, if you know it, but it is the same when we use Fréchet filter for comparison of these sequences. Fréchet filter is a set of all complements of finite sets. And when we say that two sequences are equal, when they are equal for all indexes from Fréchet filter. So it is the same way. So we get the same equality and order. So only that we can define it with help of Fréchet filter. It is important, yes, that we can use Fréchet filter and we obtain the same result. And this structure is a partial ordered non-Archimedean semiring. It's partial ordered by this order, non-Archimedean, because some sequences are infinitely less than another sequences. For instance, if I take constant sequence, it's infinitely less than the sequence 1, 2, 3, 4, 5, 6, 7, 8. Because always when I take a multiple of a constant sequence, it is less than that sequence of numbers, of natural numbers. So this is a partial ordered non-Archimedean semiring, and it is quite meaningful structure, which can be used as an interpretation of Bolzano's series. And we shall work with this structure. Yes, moreover, all Bolzano's assertion from paradoxes of infinity are valid in this interpretation. It's not. So what is our concept of size? If we wish to count a great amount of things, sometimes it can be useful to divide these things to small parts and then to count numbers of these then to add numbers of these of elements of these parts. For instance, when we would like to count all inhabitants of the earth, so we could arrange all countries alphabetically and then to count inhabitants of every country, yes, and then to add it together. So this is the idea how to count or how to express sizes of countable sets. It is similar. I would like to say now that it is similar as the so-called theory of numerosity. I don't know. They make something similar as we do here. But it is, I will return to this question at the end of my lecture, but they have the same example of the inhabitants of the earth, that's their favorite example. So, but we will say that a say is canonically arranged if there is a sequence of subsets of A, finite disjoint subsets of A, that are created according its determining ground, such that this set can be expressed as a union of these finite subsets. So we divide the countable set to smaller subsets, and then we'll add their numbers, in fact, finally. Of course, the problem is the determining ground, because it's not a mathematical definition. For instance, already natural numbers could be divided to 1, 2, then the first component would be 1, 2, the second would be empty, for instance. The third component would be 3, 4, etc. Or I can do it. And but in this case, it is quite natural to say that the determining ground of natural numbers is that in the first complement is 1, in the second is 2, etc. Now here in this case, it's quite evident, but we'll have to define it precisely. So first I speak about the idea, and when we would have this canonically arrangement, then a set side of the set A would be the sum of cardinalities, of finite cardinalities of these components. We would obtain this Bolzano series. Of course, it's yes, we can speak about characteristic sequence, and it is here A. It is a characteristic sequence. It is a sequence where for every of cardinalities of these sets, for instance, the characteristic sequence for this would be 1, 1, 1. etc. This would be 2, 0, 2, 0. And this is characteristic sequence. And finally, a size sequence is that sum of partial sums. So therefore, this is a characteristic sequence. And here in this case, it would be 2, 2, 4, 4, 6, 6. While here would be 1, 2, 3, 4, 5. So if this is a characteristic, if this is a canonical arrangement of natural number, then its size could be expressed by this sequence. It says set size or size could be expressed by this sequence. So now the problem of canonical arrangement. So we can define it for natural numbers by this way. The nth component contains exactly the number n. If two sets are canonically arranged, or if A is a subset of B, then its nth component is a subset of the nth component of B. And this is the second condition. Or also it should be valid for supersets. Of course, if I have a canonical arrangement of B, then I have also a canonical arrangement of A, but not for supersets. It's not. And moreover, a canonical arrangement of a Cartesian product. How to arrange a Cartesian product? So we use an old trick, but with a new meaning. If a set A is a union of A1 of these components, A1, A2, etc., and the set B is a union of these sets, so then we shall, in the first component of Cartesian products will be here, this A1 times B1. This is the second component. This is the third component. And this is the fourth component, etc. Yes, it would be by this way. Mm-hmm.
So it leads to the case that if I have n times n, so then this set in the
A times
n times n integers
yes,
times integers, then in fact our let's say size sequence will go as squares.
Yes, we know we need
this
squares.
Is how it has to match together.
I suppose that this is a sequence, and here it is a sequence, and therefore we always take the corresponding terms together. Yes, they
but
have the
maybe
same.
Somewhere below is in fact the idea how to measure n times n.
Yes, yes, exactly. Yes, because if we can, the same arrangement would give the right results if A and B has the same cardinality, has the same number of elements. Yes, they cannot have different numbers. They have the same number. Yes, it is important because it would work also for finite sets, and moreover, if they are disjoint and they cover the whole Cartesian product. And it would be described by this way, yes. The nth component would be described by this way, that it is maximum HA. Now, so you see, so here is a canonical arrangement. We suppose that it is like this. So its characteristic sequence is only one, its size sequence is 1, 2, 3, 4, etc. And we can denote it by alpha, as alpha. This sequence will have the number, the name alpha. It will be denoted by alpha. For instance, if I take only 3, 4, only two element set 3, 4, so then its characteristic sequence is because in the first element there is nothing, here also nothing, 1, 1, etc. and only 0. Yes. Only in the third and fourth term is 1, otherwise it's 0. Size sequence would look like this, and it is according to the threshold filter equal to 2 exactly. This is equal to 2. The complement of the same sequence would have this characteristic sequence, and this is its size, and it is alpha minus 2. That's because if this is alpha minus 2, if we take even numbers, so their characteristic sequence is 0, 1, 0, 1, and its size would be expressed by this sequence. Odd numbers, however, like this, they start with 1 when we take natural numbers starting by 1, and its size sequence like this. Of course, we can say that the sum of even numbers and and odd numbers equals alpha. It is less or equal because every element is less or equal. However, their difference is less or equal than 1. You see that we cannot compare or sets exactly. I cannot say whether it is not this ordering less than is not linear. It is only a partial order. So we have that structure. We use that structure of non-decreasing sequences of natural numbers. That is a partial ordered non-Archimedean ring. And now we can prove that when we have two canonically countable sets, then if one set is finite, then its size in this sequence, or its size, is equal to its cardinality. Yes, because it is equal from a sufficiently great index, it is equal to number of its elements. It doesn't matter how they are arranged. Only if we it was necessary if we take some finite sets. So we assume that all its elements are in the first component. If we take any, if a set is a subset, for instance, of natural numbers, then these numbers, then its size sequence is from a sufficiently great index equal to cardinality of that set. Moreover, it is valid that the size of union of two sets is size A plus size B minus size of its intersection, if possible, because every element has its fixed place. It has the place in a special components. Yes. Number three is always in component number 3. So therefore, if there is a non-empty intersection, then they would have also in the same component in A and B. And due to that arrangement of Cartesian product, the size of A times B of Cartesian product is exactly as the size of A times the size of B. It's exactly possible to count it. And what was important, that the part whole principle is valid. So it says that if A is a subset, proper subset of B, then its size is less than the size of B, and up to one element. Even in one element is important. Every one element is important. So this is some, for instance, we ask, what do you think? Are there more primes or squares? Or more primes or chi multiples? More primes. It, of course, it depends on density of these primes and squares among natural numbers, but we can count it quite easily, because, for instance, squares, these numbers, their characteristic sequence is like this: 1, then on the fourth place, fourth term is 1, ninth is 1, otherwise it's 0. So its size sequence would like this. And in fact, we can say that that the nth term of that size sequence is an integer part of the root of n, because if we take k multiples, so these are numbers like this, then always the first k, k minus terms are 0, and then k terms are 1, etc. And in fact, again, its n terms of the size sequence is an integer part of n divided by k. And for any increasing function defined on a positive real numbers, if a set A is defined by that axiom schema specification axiom scheme as the set of all n such that there is n such that n equals fn, then the nth term of its size sequence is an integer part of this. It can be said it's natural. I think it's quite clear. for prime. I have to find it, but the nth term is in fact the prime counting function, which is well known. It's possible that it can be estimated by this way, that it is the number of primes that are less than n, and their number can be estimated in these borders. So when we know all these things, we can say that the size of squares is even infinitely less than the size of primes, which is here, and it is infinitely less than the size of all multiples for any k, which can be. So it is possible to say from these easy equations. Now, what about other number structures? What about integers? Of course, negative numbers have the same determining ground according to Bolzano, or the same canonical arrangement as natural numbers, because they can be expressed like this, for instance. And when we counted, we obtain the same arrangement. Therefore, their size is equal to alpha, and the size of all integers that are unknown is 2 alpha plus 1. Is 2 alpha plus 1. So we can compare these infinite sets by this way. So here are integers, and look at the rational numbers. It's a little problem. So our aim is to express rational numbers in sum of sets as a subset of a canonically arranged set. So we start with a unit interval of rational numbers, and it is a subset of n times m, natural numbers by natural numbers, and we already know how to arrange Cartesian products exactly by this. So the unit interval can be expressed as pairs of comprime numbers such that m is less or equal than n. I write it as a fraction, but it can be written also as a pair. So their canonical arrangement is like this. In the first will be only 1 over 1, 1 over 2, 1 over 3, and n is less or equal than n. If you remember arrangement of Cartesian product, it says that in the, for instance, third component are all these numbers such that one of them, maximum one of them, is equal to 3. And m must be. And the characteristic sequence looks like this. In fact, it is 1 because here is only 1, 1. Here are 2 fractions. Again, here would be 2, etc. And in fact, it is equal to so-called Euler function, which means it is the number of coprime number less than n. It is always less than n minus 1. In fact, this characteristic function. The set size is equal also well-known Gaussian symmetry function, and it is possible to express it algorithmically. And again, we know how to estimate this Gaussian symmetry function like this, and therefore, if we denote the size of unit interval by the letter phi, then we can say that this phi we can estimate by this way. It is, and it is greater than 3/10 alpha to 2, but it is less than this amount. It is somewhere between this. So it is in order equal to alpha to 2, or less than alpha in equal. Now, what about all rational numbers? It seems to be natural to express positive natural numbers as a subset of this Cartesian product, like this, like pairs. However, yes, it is the extension of the canonical arrangement of both n and both and I, because always so far it's correct. However, when we would consider the interval of all rational numbers greater than 1, then they could be described by this way, and it is similar as that unit interval, in fact. And in this description, they would have the same size as unit interval. And it's really unsatisfactory. Yes, because it's really silly. Because there was another principle of Bolzano that all intervals of the same length should have the same number of elements. And this is not good. So much more convenient is to express them as Cartesian product of natural numbers and unit interval. In fact, as mixed fraction. Now, their set size would be like this, and we know this is alpha plus 1. This is p, and when we estimate it, so we see that we get that this borders this estimation, that the size of positive rational numbers is in fact equal in order to alpha to 3. But it is, at the first glance, it can be surprising, but in fact, it is because rational numbers are infinite to length, but also into the depth. So therefore, it makes sense that this is this it's like this. All rational numbers, of course, it's easy to count it. It's similar. They would be all rational numbers. It is it is less than alpha to 3 and greater than 3/5 alpha to 3. This is quite a rough estimation, but however, and it has the same reasoning. And moreover, it's not here, it's possible to prove that all intervals of rational numbers of the same length have the same size. They all really, if we take all unit intervals, have the same size, and then all intervals of the same length have the same size, which is very important. And it also is consistent with that Bolzano's request on intervals of quantities. So this is yes. Now I finish with this theory. Now I would like to compare it with a theory of numerosity that it is started in 2003. The first paper was from 2003, Numerosities of labeled sets, and 3 years ago, how to measure the infinite mathematics with infinite and infinitesimal numbers is the book. This is the book. So they use so-called labeled sets. They are in principle the same thing as canonically countable sets. What is important that they used for that equality and order, instead of ratchet filter, they used the ultrafilter. It has its advantages and it has its disadvantages. The main advantage is that numerosities, the same as sizes of these sets, are linearly ordered. They are linearly ordered, but they needed these mathematicians. They needed because they use it as a basis of so-called alpha calculi. It is a special type of non-standard analysis. So they used to be linearly ordered. But when when I wish only to express sizes of sets, so maybe the linearly ordering is not necessary. Because, for instance, they ask about question if all natural numbers in the numerosity of all natural numbers is odd or even. Here, in my comparison, I cannot say because I don't know. But it depends on ultrafilter which they choose. If they take an ultrafilter such that even numbers are elements of these ultrafilters, then natural numbers are even, otherwise they are odd. Many results depend on the choice of an ultrafilter. Even they take special ultrafilters, such that, for instance, or K multiples are in that ultrafilters. However, still many properties are undecided, and we don't know what they are valid. There are some basic notions are defined, only defined, they defined it. They don't justify it, while here we justified it. Moreover, their assumptions are arbitrary. For instance, they write themselves that they don't know how to express the number of elements of unit intervals, and for instance, they can state it as alpha. But I think it's contradicts to it that it is to this our theory. Yes, and moreover, yes, these results which we obtain by using Freshet ultrafilter are valid in all extension to any ultrafilter, and therefore they are always valid. Yes, they are undoubtable. While when ultrafilter always depends on that which and moreover ultrafilter, maybe you know, is a non-constructive object, and its existence depends on the axiom of choice. Quis pro quo. So here are on some more literature. This is on Bolzano's mathematical interpretation of Bolzano's mathematical infinite. I have also a paper on Bolzano's on the interpretation of Bolzano's paradoxes of infinity. Yes, it was my inspiration. And here is also another paper, important paper from Paolo Mancosu, who writes about measuring the size of infinite collections. Was Cantor's set theory inevitable? It is another source of my inspiration. So thank you for your attention.
Any questions?
Yes, I would like to ask you, is it possible to use this estimation of number of rational numbers, natural numbers, somewhere in computer science?
I have a question, maybe purely mathematical, but if you have n squared, that means all pairs of natural numbers, and you cut off
all pairs of natural numbers,
only coprime. Mm-hmm. So this set in your way of thinking is larger than the set of all rational.
No. Only from 1 greater than 1. All numbers.
Yes, but let's say I have all rational numbers that are positive. Mm-hmm. Positive rational numbers, and I would like to compare them to the pair of natural numbers that are coprime, because this is the way how I represent rational numbers that are not negative. So I guess that in this comparison, the set of pairs is maybe larger, because I put there also, because I put there always, for example, at the stage n, I put there all numbers, which is the let's say the ratio of two numbers that are, I can have a larger number on the top than on bottom. Like denominator, how is it? Numerator can be larger than denominator.
Yes, maybe I understand you.
So if you can
For
make it
instance,
clear.
yes, therefore, it's not a good idea to represent, for instance, 5 divided by 2 as 5 as
Yes, I
but
think
it's
that
but better way is as 2 1 2 as the triple 2 plus 1/2. Yes, so there it depends on the representation of mathematical structure, and I wanted to show, or I wanted to demonstrate that it is much more suitable to represent rational numbers not as pairs of natural numbers, but as triples of natural numbers. In fact, as a mixed fraction.
I understand it, but can you tell
Like
me
this.
which is larger, which set is larger?
Yeah, which this one or which?
No, if I have pairs of integer numbers which are coprime, this is a set, and I think the theory can measure the size.
With this one?
No, simply what is compare these two, or maybe compare these two representations, yes, which is more dense, let's say.
Yes, it is of course the set of these. This would be, in fact, it would be alpha. And
Of order, let's say, because it's not exactly. If I cut off coprime prime.
yes, it is.
Partially.
Yes, of course.
Prime numbers, so it's
Or
not exactly. Okay.
Yes, but
I see. This is not.
Yes.
Not explaining.
Yes.
What's going on.
Something like this.
Thank you.
I had a question whether there is some relation to descriptive complexity of sets or something like that.
No, I don't know. That's what I don't know.
Is your description working well with power sets?
No.
Of finite
Because
of finite sets.
Yes, of finite sets probably yes, because finite power sets of finite sets are always finite. Yes.
So there shouldn't be any problem with that.
Yes.
Okay.
Of course, with power sets of infinite sets, it wouldn't work because they are not countable. Yes, and moreover, it also cannot express ordinal numbers. Yes, because the existence of ordinal numbers is strongly dependent on Cantor's principle. So it's not too.
One maybe more provocative question. What was the advantage of not having zero among natural numbers?
No, because I know I can say you because I have because I start with a sequence and I would like to have the first term of the sequence A1 and not A0.
But I think that's here the answer might be even more simple because you want to count the number of whole numbers. Okay,
as a union of integers, negative integers, and 0. If you have an overlap over there, you can get problems.
Oh, you get -1 instead of +1.
Sure, but
-1 is not good.
Other questions? Right, so let's bring the speaker again.